Alright, another draft physics presentation. Draft science. Same difference, mostly. Alright, so this is the Pake Physicser of the Week award. Will go to Richard Feynman in honor of a comment by some viewer who was pointing out how, everybody has to go see Richard Feynman videos. He's just so brilliant. And Piro, and this whole two-slit thing. So this is a long video. It's an hour, and I'm probably going to do the whole thing eventually. So this might be a really long video. I may do it in pieces, but it's really important. This is the foundational experiment, and in the history, again, Newton first discovered this phenomenon by using a hair and small apertures, perfectly aware of the pattern created, the pattern, and also aware of the fact that there's another phenomenon that takes place, which is the idea that the light diffracts, that it spreads. So, and what basically happens in the single slit is, as if you make the slit smaller and smaller, the light spreads more and more, but there's a pattern, and the pattern just gets bigger and bigger and bigger because it's spreading. And so the patterns always diffract. There's always diffraction as part of the pattern, depending on how wide the openings are. Now you could argue that there's very little that's all that interesting. It's an interesting phenomenon, yes. Newton's rings. Newton didn't have a good answer. He argued with Huygens about different theories. They sort of got caught up in this idea of the speed of light and arguing that light goes faster or slower. And I would argue that those were wrong ways to think about why the light diffracts, why it changes its course. So yes, and this is a long time ago, 1650, long time ago, Newton. And so you can understand some lack of insight. Then Young came along in 1801 and did basically the same kind of experiment, got a really cruddy pattern, didn't get the full two-slit pattern, that is the pattern with an inside another pattern. Nothing remarkable, and then as time passed, and Young was a devotee of wave theory, a Huygens fan. Then around 1925 or so, a group of physicists decided what the truth was going to be. Feynman included, I guess, with some of it. That's all. They decided we're going to draw conclusions about what's causing this pattern, or we're going to force there to be an answer to the question that was a mystery, just basically. And it's strange, and it's hard to come up with some kind of one physical answer that explains what's happening. But that's just because we don't have a whole lot of information about what a photon is. And most of the descriptions of photon, just even using the word photon is sort of a mistake, because there's a length to the ray of light that is perceived. To call the something with a frequency, something with a wavelength, a ton, is a dangerous thing to do. But these are all conclusions they drew in terms of how they were going to force the model. And again, it's just a tiny group of physicists who basically decided this is going to be the story. And so it wraps up in Heisenberg and some of these big name characters. And they've basically told us what the truth is. And their truth is not anywhere near a complete answer. I would argue that in many respects, my initial reaction is it's silly. Doesn't make any sense. I don't think the universe works that way. I think that's essentially what Einstein was saying in terms of spooky action was his kind of rhetoric, and I don't know exactly what his initial reaction to forcing, wave particle dualities. He eventually conceded that he can't do any better, so you're stuck with it. But that's all these people are saying is, I can't think of an answer, so therefore there must not be one. And that is the arrogant part, and we're just living on that pile of arrogance, that there can't be a better answer. And I would argue that there's better answers than bent space. There's for gravity. There's better answers for magnetism than virtual photon. And there's a better answer to why photons and electrons and even atoms are affected when they pass materials, atomic substances. That there's mechanical theories that can explain what's happening. All right, that's probably enough of a preface. But again, it just has to be understood. This is just Richard Feynman saying, we're the pros, we've decided, and you better get used to it because we're going to keep telling you this is the truth. Essentially, that's all there is until you can tell us better. And I don't think they really listened to anybody else anyway, so I don't think anybody would even have that opportunity.
In the beginning of the history of experimental observation or any other kind of observation on scientific things, it's intuition, which is really based on just experience with everyday objects that suggest reasonable explanations for things. But as we try to widen and make more consistent our description of what we see, as it gets wider and wider, and we see...
So let's understand. See, the problem is they just weren't coming up with an answer. No answer fit for hundreds of years, right? So this is a problem. It started with Newton, and it stayed there, staring them in the face. And eventually, I guess by the 1900s, they're just saying that we're just too smart to be stuck by this, so we're going to force an answer. And in my opinion, they forced a wrong answer.
See a greater range of phenomena. The explanations become what we call laws instead of simple explanations. But the one important odd characteristic is that they often seem to become more and more unreasonable, and more intuitively far from obvious.
Right. So maybe that should be a signal that maybe you're going down all kinds of wrong roads. So you glued yourself to this bent space, to relativity, based on scant evidence. The Eddington experiment was really poor. The rest of the evidence is really inconsistent. And then you have such bad evidence, in terms of explaining exactly why photons do these patterns, that you were stuck with wave-particle duality, pretending the thing has two different, completely fundamentally different properties, conflicting properties. And maybe that should be a sign that, yeah, maybe you're thinking the wrong way. You started with the wrong premises.
The second example is the relativity theory, in which, for instance, the proposition is that if you think that two things occur at the same time, that's just a subjective opinion. Someone else could conclude that those two events, one was before the other.
Right. So he's saying that somehow you can actually physically do something where you could reverse events, where you could see somebody die before they were born. Nonsensical notions that just can't be the truth. And yet they're playing with that idea like, well, maybe this is possible. Where it's not possible, and there's no evidence that it really does happen. It's just plain speculating. And it's not even within a rational confine. It's not even bounded by what we do see everywhere else in the universe. And we have no reason to expect the small universe to play by different rules.
And that simultaneity is merely a subjective impression. Now, there's no reason why this should be otherwise, really. The things that the direct everyday experience involve large numbers of particles, or involve things moving very slowly, or involve other conditions that are very special, and represent, in fact, a very limited experience with nature. It's only through, it's a small section only that one gets of natural phenomena from a direct experience. It's only
So again, I would argue that's not true. We see all kinds of phenomena right in front of us. We measure the gravity all the time as something real, okay, and they've turned it into some sort of geometry, you know, as an explanation. Again, we can watch magnets do what they do, and they're telling us, well, something that doesn't really exist, some virtual thing, is doing something. Well, you know, we know, but that's not an answer. That's an evasion of an answer.
It's only through the refined measurements and careful experimentation that we can get a wider vision. And then we see...
Yeah, but that's the whole problem. There's only a limited number of experiments you can do. And I would argue that they haven't done a lot of these simple experiments with much imagination. They haven't teased as much information as they could have out of the experiments by doing them in enough variety of ways and doing them meticulously, you know, getting really good statistical data. And they really haven't, because they have a theory of how it works, and so they just do theoretical thoughts about what it will do instead of actually doing it. But again, very little hard evidence, and they're drawing hard conclusions.
Unexpected things. We see things that are far from what we would get. We see things that...
So it's not that far. So again, let's understand that the double slit pattern is the simplest pattern you can make, you know, on, off, on, off, on, off. Not very sophisticated. And why shouldn't we have some notion that when some force, photons or electrons, something, is passing through a surface area, a place where there's atoms, that it might be affected. When we know if we pass light through water, it gets diffracted, gets bent. We know that rainbows are created by that way. We know prisms. There's lots of mechanisms that are separating light or bending light. So it's not that big a surprise that apertures would do the same thing. Making more of the energy pass by a surface would make more of the energy be disturbed by the process. I mean, that's all that we really have as a fact, is that something disturbs the straight line force. We know the force, generally speaking, is a straight line force, and for some reason the straight line is being changed, the direction of the line. But that's all we have as real evidence.
They're very far from what we could have imagined. And so our imagination is stretched to the utmost, not as in fiction to imagine things which aren't really there, but our imagination is stretched to the utmost just to comprehend those things which are there. And it's this...
Yeah, there's always catches to things, okay, and any kind of solving any kind of mystery. I mean, a murder scene, whatever, there's lots of situations where it can be quite difficult. There's very little evidence, and you know, it's all very subtle, and you know, it's going to take time to find the answer, and people don't want to take time sometimes. Sometimes they don't want to wait for the evidence. They want to jump the evidence and get to the answer.
Kind of a situation that I want to talk about tonight. Start, for instance, with the history of light. At first, light was seen to behave, it would appear to behave very much like a rain of particles, of corpuscles, like rain. Bullets from a gun, same idea. And then with further research...
Right, and that was 350 years ago, and that idea hasn't been revisited, hasn't been really thought about, because even when they say it's particles, they're not thinking about bullets at a frequency. They're thinking about some other kind of stuff, you know, some long bullets as long as the wavelength, or some other kind of weird thing. But they're not really thinking about cannonballs or bullets coming at a frequency.
It was clear that it was not right, but the light actually behaved like waves, like water waves, for instance. And then in the 20th century, on further research, it appeared that light actually behaved in many ways again like particles. In the photoelectric effect, you could count these particles, they're called photons now, and so forth.
So again, the photon, as the word's used, isn't really a particle, because a bullet by itself can't have a frequency. It has to be more than one bullet for there to be a distance between them to say there's a frequency. So again, so they start off with, in my opinion, the right idea that it's bullets, but they lost that idea when they said photon, that is the thing that actually an electron can understand. And the electron can't understand a single bullet. It doesn't mean anything to it. It has to get hit by more than one for the electron to have the reaction where it produces frequency back. It has to have frequency in to produce frequency back, and what we're receiving, what we detect, is the frequency that the electron produces as a reaction. That's all we can do, is detect the energy the electron gives back.
Electrons, when they were first discovered, behaved exactly like particles, bullets, very simple. Further research shows, in electron diffraction experiments and so on, that they behave like waves.
So again, the same argument that because of this experiment, because you shoot electrons through next to a surface where you would expect there to be a confused nuclear circumstance. The atoms don't create surfaces. Okay, atoms have electrons and protons that are mostly made out of empty space. So a surface isn't some kind of hard thing. It's a complex mixture of things, and it doesn't shock, okay, somebody who has a little bit of mechanical knowledge to understand that mixed place, that place where there might be a lot of free electrons, for example, would cause an electron to be scattered.
And as time went on, there was a growing confusion in the question of how the thing really behaved, the waves or particles, particles or waves, and everything looked like both. Now this growing confusion was resolved in 1925 or 26.
So let's understand the confusion comes just because there is a similarity. The pattern, okay, is the on-off. It is a pattern that waves create, okay, water waves, in certain experiments. So, in particular, in two-slit experiments. Now, if you do a single-slit experiment with a wave, you don't get an interference pattern. You just don't. The wave just comes out in nice, straight waves. I mean, bent. I mean, they're spheric. They're circular, but they're even and proportional and symmetrical. They come out as symmetrical waves. There's no water wave correlation to the single-slit in light. Single slit in light, you got bars. You got on and off. You don't have it in water waves. Now you do have it in the two slit, and then you lose it again when you have multiple slits. Water doesn't do what light does, which is send an image to specific locations. So it matches in one case, and it doesn't match in the other cases. So let's understand that the evidence is confused at best for any wave theory, because there isn't any consistency. It doesn't match in most wave experiments, don't match what light does, and it certainly doesn't match in the fact that the wave goes up and down. It goes very high and very low. It has a change in its amplitude, and then no change, and then change, and then no change, where light's going on, photons, and no photons. Light isn't going blinking on and off. So it doesn't match in other ways.
With the advent of the correct equations for quantum mechanics, and now we know how the particles, how the electrons...
So again, that's what they call the Schrodinger equation or the wave equation, and it's basically just it's the mathematical equation for phase changes, and phase changes will create the same effect. And so you could, I have argued, they think in radar gun experiments that the Somehow it's interference that's creating the pattern. But using exactly the same mathematical formula, you would use it for jamming. That the signal's merely unreceivable. It's not that there's no energy there, it's that you can't receive it with the equipment we use to receive radio signals. You can't detect it. The energy's there, it's just not in a form that can be detected by tuning in a radio receiver. You have to use some other way to measure the energy that doesn't depend on tuning to a frequency. But it's the same mathematics. So this isn't, quantum mechanics isn't some special kind of math. It's doing very simple math in the sense it's just geometry. It's just saying that if you have, two frequencies and one of them has to travel a longer distance, its phase will be different than the other one. Nothing more complicated than that. It's not a mystery equation. It's really dirt simple.
How light behave. But what can I call it? I can't say they behave like a particle wave, or they behave in typical quantum mechanical manner.
So again, he's calling it quantum mechanical, but there's no, like I said, this is algebra. This is geometry. There's no quantum mechanics to the Schrödinger equation. There's no mystery to it. It's just simply a phase equation. I mean, it's really dirt simple. It can't, you wouldn't call it something new. And you certainly wouldn't use quantum mechanics, which, that term, just because it was quantum electrodynamics was the original subject. And so clearly it has, the subject has everything to do with just photons interacting with electrons. It really doesn't have to do with electrons reacting with electrons, or buckyballs or atoms reacting to electrons. So this expansion is just there's no logical reason to do that.
There isn't any word for it. If I say they behave like particles, they give the wrong impression. If I say they behave like waves, they behave in their own inimitable way.
Which they haven't explained. So again, they're just saying that we jumped on this bandwagon. So they jumped on bent space as an answer, bent geometry, whatever, pulling gravity. They jumped on relativity, like somehow velocity isn't real or absolute, that somehow you can be in different frames and somehow be traveling, you can break rules like the order of events. You can end up seeing somebody die before they're born, which, again, is illogical.
Technically could be called the quantum mechanical way. They behave in a way that is like nothing that you have ever seen before.
So again, when the truth is revealed, it will be a truth where I think it's going to be just the same thing as saying, well, what do you mean we never saw it before? We saw light get bent when it went into water. We saw it do, bend differently when it's going from a dense material to a lighter material. So we've seen the source of this before. We've seen elements of it before. So that's sort of an exaggeration.
Your experience with things that you have seen before is inadequate, is incomplete. The behavior of things on a very tiny scale is simply different.
So he's saying it is, but I'm saying that's just him saying it, right? I mean, we really don't have any proof that the answer has to be confusing and nonsensical. It can be dominoes, it can be bowling balls, it can be cannonballs, it can be something as simple as cue ball hits 8 ball, and it can be that. The answer can be that simple.
They do not behave just like particles. They do not behave just like waves. Atoms do not behave like weights hanging on a spring and oscillating, nor do they behave like miniature representations of the solar system with little planets going around in orbit.
Yes, and they don't behave like carrots. And yeah, I can list all kinds of bizarre, stupid things to sit there and say that it's a... But, we don't. Again, they have no evidence. They just have a pattern, and a very simple pattern. And he's saying something simple can't make the simple pattern. It's just they didn't think of it. Something very simple can do it. I mean, I provide a simple model for magnetism that completely explains why there's attraction and repulsion. It's incredibly simple. It's as simple as white and black pieces on a chessboard. Not complicated at all. Or more precisely, a checkerboard.
Does it appear to be somewhat like a cloud or fog of some sort surrounding the nucleus? It behaves like nothing that you've seen before. Well, there's one simplification. At least electrons behave exactly the same in this respect as photons. That is, they're both fluid.
So, okay, they don't exactly behave the same way. So, again, this is, okay, how much can you fudge the truth here? What's the legal boundaries of calling something exact or the same? I think in this case it's important to make the distinction that as you make the thing bigger that you're throwing at the slit, the effect is reduced, and rather dramatically. So the photons have the sharpest image, the electrons is duller, and if you get into anything bigger like atoms, it's even duller in terms of the effect. The noise level to signal is 70 to 30. I mean, it starts to get where the amount of deflection is so tiny that it's almost imperceptible. I think it's important to point that out.
But in exactly the same way. How they behave, therefore, takes a great deal of imagination to appreciate, because we're going to describe something which is different.
See, there'd be little similarities. Like, see, they've pretended that electrons now, because of de Broglie, one of these little people gets to decide what the truth is, that they've assigned frequency to a kind of intensity, because it works that way with light. So they've given everything else in the universe a frequency when it doesn't have one, a wavelength, an artificial one, because light has this association. So now instead of having a momentum, instead of a car going 60 miles an hour, it has a wavelength of whatever, 60 feet per second or whatever. And it really doesn't. There's no wavelength, there's no frequency, it's not a reality. So the trick is with electrons, it's their momentum that'll decide how much they're diffracted. So the slower they're going, you can understand the more they'll get deflected. The faster they're going, the less they get diffracted. So it fits the mathematics, because the mathematics basically says the higher the frequency, the narrower the beam, the lower the frequency, the wider the spread. So it fits, but it fits for completely different reasons.
Anything you know about. This, in that respect, at least, makes this perhaps the most difficult lecture of the series, in the sense that it's abstract, in the sense that it's not close to experience.
Yeah, no, what it is very tiny amounts of evidence, little tiny indications of a function, of a property, little vague, foggy images of properties, and them forcing that to be conclusive evidence. And they don't have that, they didn't have that in 1925, and they just decided for all the rest of us that we're going to commit, and they shouldn't have. Because they committed to the wrong answer.
I cannot avoid that. Were I to give a series of lectures on the character of physical law, and to leave out from this series the description of the actual behavior of particles on a small scale, I would certainly not be doing the job. Because
so he's talking as if he has some knowledge of the actual behavior, when he's basically saying, we don't know what the actual behavior is, we're just going to call it random power, or special pattern making. They don't explain how it happens at all. So they're just declaring it a magical thing rather than a cause and effect event.
This thing is completely characteristic of all of the particles of nature and is a universal character. And it is, if you want to hear about the character of physical law, essential to talk about this particular aspect.
So again, he's saying it as if there's a law here. There are no laws governing any of this. Beyond the fact that there's a pattern. That's it. The law is there will be effects if you force photons or electrons close to surfaces. And the effects are stronger depending on how the surfaces are placed. So if I have one surface and I shoot light, I'll get a very weak pattern, deflections. Now if I have two slits facing each other or coherent to each other, I'll get more pattern. And if I have even more slits close to each other, I'll get even more pattern. So the idea is that the slits affect each other. The surfaces are connected when they're close. And that is perfectly understandable as a charge phenomenon. Surfaces charge. On most all substances will have a charge to the external world. Most of them will likely have more electrons on their surface and create a negative surface as a preference. You can just think of it logically, that if they have any proton exposure, that exposure is going to attract electrons. Just the way the atoms work. The positive stuff's in the middle, the nucleus, and there's always extra charge that reaches out. Just like our solar system has extra gravity that goes beyond the last planet, Pluto or whatever. There's still gravity out there. It's not strong enough to hold a planet, but it's strong enough to hold a comet.
So it will be difficult. But the difficulty really is psychological and exists in the perpetual torment that results from your saying to yourself, but how can it be like that? Which really is a reflection of an uncontrolled, but I say utterly vain, desire to see it in terms of some analogy with something familiar. I will not describe it in terms of an analogy with something familiar. Not to be.
That's merely because he doesn't know what the answer is. He doesn't know whether it's dominoes or pool balls or waves, which doesn't, like it's not, waves aren't an elemental explanation. All the waves we know of don't happen as part of elemental physics. They're an emergent property. They happen in mediums where atoms are bound to each other. You don't have waves in things that aren't bound to each other.
There was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read it, a lot of people kind of understood.
So again, this caught on to a virus, a sickness in a sense. It's a wrong answer. Whatever.
Understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics.
So, yeah, these are all funny jokes, but I'd say that's a serious defect in the theory. If it has that lack of coherency to what we do know, what we can see, and we're living in a world where everything seems quite governed by non-magical truth. You don't play the piano unless you practice. You don't do this. I mean, it's causes and effects. There's just no magic in it. And yet you're essentially declaring elemental magic. I don't think there's a reason to do that. And I think there's a very significant reason to only do that as a last resort, not a first resort.
Now, if you appreciate this and don't take the lecture too seriously, that you really have to understand in terms of some model what I'm going to describe. And just relax and enjoy it. I'm going to tell you what nature behaves like, and if you will simply admit that maybe she does behave like this, you will find her a delightful, entrancing thing.
Which is just baby talk. I mean, I just sort of insults my intelligence that I'll enjoy hearing a religious story. I'll enjoy something that doesn't make any cognitive sense, that just sounds like fairy stories. I don't like Three Bear stories.
that's the way to look at the lecture, not to try to understand. Well, you have to understand English, of course. But in any sense, in terms of something else, don't keep saying to yourself, if you can possibly avoid it, but how can it be like that? Because you'll get down a drain. You'll get down into a blind alley. Which nobody...
Right, a blind alley that they failed to come up with the answer. So again, this is really just about, these guys are smart. They say, if we can't think of what the trick is, there's nobody else can. You know, it's just kind of obvious. They're saying, oh, no, don't trouble yourself with the fact that it sounds stupid. You know, that sounds incomplete, or it's got to be wrong somehow. There's got to be a better answer. No, don't do that. Because, you know, we did that. And we couldn't do any better than this slop. So you're dumber than us. You can't do any better than this slop. Which, you know, again, that's the arrogance.
You get escape. Nobody knows how it can be like that. So then just let me describe to you the behavior of electrons or a photon in their quantum mechanical way.
All right. Now, my criticism is this description will not be accurate in significant ways. I mean, some of them are insignificant, but I'm just mean taken together, these little inaccuracies add up to a big inaccuracy in terms of realizing conceptually that there is no evidence, hard evidence of anything, and that they claim certain probing of the experiment that they never did. And so it's a very distorted view of the actual experiment and the actual history and why they drew these conclusions. All right. Well, probably enough for this part. I will return and such. I think we're continuing with Richard Feynman, and I have no idea where I left off. So let's continue.
The way I'm going to do this is by a mixture of analogy and contrast. If I made a pure analogy, we would fail. So it must be by analogy and contrast to things that you're familiar with. And so I make it by analogy and contrast first.
Right, well, oh, come on, YouTube. Well, it's interesting. Not really. Yeah, fix things, Gary. Probably could get rid of this also. Oh, it's in the way. Probably don't need this either. Alright, I'm wasting your time, sorry. Yeah, this is way out of position. Okay, that's better. Be a professional. Or not. So, I hope this is going to play without having to reload it. Yeah, so analogy and comparison, I think that's what he said, or contrast, yeah. Yeah, that's all we got. I mean, we invent a word, and then we use that word, and then we invent the word wet, and then we say, yeah, what are things that seem wetter than other things? And so you have to have, you know, in the same process here, you're saying that mechanically we see things. And I would argue that this is kind of fundamental to what physics did, but it's kind of understanding that what we see is things have to interact. That is, they do have to interact. They have to, in some way, hit. Meaning, and they can hit their gravitational field. They can hit the radiation something is producing, like a light or a piece of radioactive material spewing something, and that spew can be an interaction. But there has to be an interaction, and so in a sense it is all push in terms of what we actually see. Everything we do that seems pulley, you know, there's a push. That's just, I think, true. I don't think anybody can show me evidence of something that's a true pull. And yet they went with a theory that just plays pull games, and that's just, you know, a fundamental mistake, just rudimentary mistake.
First, to the behavior of particles, for which I will use bullets, and second, to the behavior of waves, for which I will use, say, water waves or sound waves. So we begin. First to discuss in a particular, what I'm going to do is I'm going to invent a particular experiment, and first tell how it would behave, what the situation would be in that experiment using particles, what
The fundamental mistake will be in this analogy is that he gives no properties to surfaces. So, as we know, the nuclear world is not like our world. Okay, there's no surfaces. There's no flat walls. There's no benign surfaces. There's no surfaces that aren't radiating something. So we're clearly radioactive in the sense that we're producing heat versus our environment in most cases. And even when it's the other case, then we're absorbing heat from the environment. There's real interactions going on in the nuclear world. There's a lot of stuff happening. And he's going to use an analogy where he just has walls and bullets, and there can't be any interaction. And I just would argue that's a fundamental mistake, a fundamental wrong analogy, because we have no reason to believe that atoms create solid surfaces, so to speak, because we already know the atoms are mostly empty space, and we know they're made out of discrete little things in a bunch of nothing, and that can't be a solid surface. It's got to have some elasticity to it, elasticity. Just logically, you can understand that surface has got to be, like I said, when we hit something hard, we say, but there's really not something hard there. The electrons are a little bit soft in the sense they're in tension. And yeah, we perceive it as being solid, but there's a whole bunch of intrusions, penetrations of the actual matter.
What you would expect to happen if waves were involved, and then what happens when there are actually electrons or photons in the system. And I will just take this one experiment which has been designed to contain all of the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and peculiarities of nature 100%.
Now, that's just a way overstatement in the sense this can't be 100% analogous or complete because you didn't include all of the complexity of the nuclear world. So it's kind of like thinking about gravity in terms of only thinking about it by analogizing it to something that actually has to hit something else. When we know that most of the gravitational interactions don't require two bodies to actually hit each other, they're just going to be bent and twisted by the interaction with the forces being created, the changes in the force field, the changes in the geometry, however you want to think about it. But it's the change in geometry that does most of the bending, not an actual impact.
Any other situation in quantum mechanics, it turns out, can always be explained afterwards by saying, you remember the case of the experiment with the two holes? It's the same thing. And so I'm going to tell you about the experiment with...
Right, so again, it's a foundational experiment, and they should... you should be pretty explicit and accurate. Not a complex experiment. So again, why leave out fundamental facts that you know about the real world? In terms of Newton had already discovered some of these facts, and then we discovered more facts. Newton didn't know atoms were 99% nothing.
With the two holes, which is the general mystery, does contain the general mystery. I am avoiding nothing. I am bearing nature in her most elegant and...
Yes, what you're doing is describing it, though, in a way that makes it seem mysterious. So you're forcing a mysterious description where you could just say, well, look, it's the simplest pattern in the universe, on-off. So let's not pretend it needs to be a complex cause. It doesn't have to be anything mysterious or weird because it's not a very complex pattern. But they don't do that.
Difficult form. They start with both. And all the experiments are going to be in the same general design, so I'll draw it this way. Suppose that we have some source of bullets, which is just represent the source, which we call the source, and is in fact, in the case of bullets, a machine gun. Then we have a plate in front here with a hole in it for the bullets to come out of, and this plate.
So this is never really explained why this plate exists. Why in the traditional experiment the light or the energy is passed through a small aperture and then passed on to the small apertures. Whether it be a single slit or a double slit, they essentially do a two-slit experiment both ways. So just saying, it's never explained why the necessity for that first aperture. I would argue that for viewing purposes in before the 1900s it was sort of necessary, I guess, because you couldn't get straight lines of light, straighter lines. You'd have too many angles coming into the two-slit experiment.
Plate in the case of bullets is armor plate. Then a long distance from here we have another plate, which I'm drawing only a short distance because I haven't got room on the blackboard for everything, but this distance is supposed to be much longer in proportion to the width. Please expand that. That's a small point. And it has two holes in it. That's the famous two-hole business. I'm going to talk a lot about these holes, so I'll talk about this hole as number 1 hole and the other hole as number 2.
Again, if you use holes, then you're going to get Newton's rings. You're getting patterns in all directions. So this is another thing that, they don't really get to the truth here much in terms of explaining what you're going to get as patterns. What the slits do is if, that little hole, the aperture, creates a beam that's only spread so much. So you're spreading it this way. Instead of having the light come in all kinds of directions from the outside in, you're forcing the light to be coned from a point source, so you have some control over how much light gets to your aperture. But if you don't have a longer than wider slit, then you end up having the diffraction in all directions, and you end up having a pattern in all directions.
And I'm only drawing it in 2 dimensions. You can, if you wish to imagine these as round holes in 3 dimensions, but just say it's a cross-section. And then again a long distance away, but we'll draw it relatively short distance because of the limitations of this blackboard. We have another screen here, which is just a backstop of some sort, on which we can put in various places what I will call a detector. And we'll mark that detector, which in the case of the bullets is a box of sand into which the bullets will be caught, and we can count them. That's the detector for bullets.
So it sort of makes it more complicated than it needs to be, in the sense that you could just say you put a target, a piece of paper, and you're just going to see where the holes get punched in the piece of paper. And obviously that's not ideal because there might be holes in the same locations, but it, generally speaking, will reveal your pattern. So in other words, you can just use a piece of photographic film and collect the photons.
I have to redraw the experiment each time, so I'll label everything in this way, and then we'll be able to catch on to situations for different cases. And also, I'm going to do experiments in which I count how many bullets come into this detector or box of sand when the box is here, or here, or here, or here. And to describe that, I'll measure the distance of the box from somewhere down here and call that X. And I talked about what happens when we change X. You need only to move the doggone thing up and down. All right. Now, first, I would like to make a few modifications from real bullets into idealizations. The first is that the machine gun is very shaky and wobbly, and that the bullets go in various directions.
Right. Now, if we could control photons, see, the idea would be if we could control the direction of photons and electrons explicitly, and well, electrons we do have some control, you could just shoot them through the two slits on purpose and make sure that you shoot them through the two slits in a random order. That is, you shoot just as many near one slit as, one surface as the other surface. And theoretically, there's absolutely no reason why you shouldn't get the appropriate pattern. And so if you could do it with bullets, it would be an ideal, because then you could just shoot it through one of the slits. You'd know what slit it went through, you know exactly what position it went through, and you'd know exactly where it went. And that would be very convenient. And so the only limitation here is just that we don't have the technology to arrange atoms so precisely that we can dictate where photons, how they're produced. They're produced in a radial random form from atoms inside of warm materials that are moving too much, so we can't predict any one photon what direction it's actually going to travel in. Now maybe we could get them cold enough, maybe we could.
Not just exactly straight on, but in fact. And they can ricochet off the edges of the slits, the holes in these armor plates. And
so again, this ricochet argument, but it's an important argument because he's using it to claim ricochet. Well, that we could dictate by how thick we make the material. So the steel plate, we could make it very, very thick, and then we could cause more ricochets if that was an issue. And we'd get different results, and we really don't. You destroy more bullets, so there has to be some, but it doesn't disturb your end results any. And these are all really, I'm just saying, these are important details. This is why this video could take a long time, but this is all part of what needed to be stated here as a context, is that these analogies are not comparisons to what's happening on the subatomic level.
Finally, well, let's say, for instance, that the bullets have all the same speed or energy if you want, but that's not very important.
I mean, let's have the context, and let's understand that we already do know, it's pretty reliable science, that photons are scattered by hitting electrons. They hit electrons and they change their direction. The electron gains some momentum, the photon is, you could argue, readmitted. It's absorbed and then readmitted, and it's readmitted in a new direction, and we call it scatter. So we know that photons are very easily changed in their trajectory by electrons. And again, this gets back to the nuclear argument. What do you think is near the surface of materials? Well, I think you should think electrons are near the surface of materials.
But the most important idealization in which it differs from real bullets is, I want these bullets to be absolutely indestructible. So that what we find in the box is not pieces of lead of some bullet that's broken half, so we get the whole bullet, please. So imagine indestructible bullets or hard.
Alright, so this is another place where the analogy sort of again breaks down, because again the word photon doesn't really fit with bullet. Even if you're a particle person, you have to recognize again that electrons are reacting to something more. They're reacting to stuff coming at a frequency. Because if I change the frequency, I can change the reaction of the electron. So clearly they're frequency dependent, which means they have to be hit by more than one bullet. So you have to fire 2 or 3 at something to make it do, to tip it over, to create the reaction that'll create the reaction. Okay, so the action you create has to be created by a little bit more than just one bullet. One bullet is gravity. You can't see gravity in this tiny amount of energy. Light is so weak compared to the gravitational force. Again, we know gravity does this with no problem. This is heavy. If I had to move that with photons, incredible number of photons would be necessary.
Hard bullets and soft armor plate or something. And now the first thing that we will notice about bullets.
Just trying to say that, you know, when you think about gravity, they keep saying it's a weak force. But that's incredibly strong force, and compared to what a photons can do. So I'm just saying, if you were to lose a little bit of photon energy to gravity, like you create a little tiny bit more gravity, the amount of extra gravity, you know, if I push this just a tiny bit faster, it would be such a tiny, you need so many photons to do that. So just a couple of photons and you'd never be able to tell a couple extra photons hit this, because it's being moved by such a strong force.
Is that the things that arrive come in lumps. when the energy comes, it's all in one bullet full of bang. If you count the bullets, there's 1, 2, 3, 4 bullets. The things come in lumps. They're equal in...
Yes, but they're not equal. Now, I would argue that the quanta is equal. The bullets are equal, but changing the frequency changes the effect. Clearly, a phenomenon we know that's an electron sensitivity. Electrons do that. Hit them with different frequencies of light, they do a different thing. They change the direction in a different amount. That's known physics. So I'm just saying it's nowhere in this context. This is supposed to be quantum electrodynamics, quantum mechanics. It's supposed to be the subject of photons and electrons and their interactions. They're bound to each other in such a dramatic way in physics. And it's not part of this elemental discussion at all. You won't hear in the photon experiment any mention of electrons, and you won't hear any mention of photons in the you get it. Between the two experiments, they'll never talk about the interaction.
Inside, we suppose, in this case. And when a thing comes into the box, it's either all in the box or it's not in the box. It comes in lumps. More. If I put up 2 boxes here, I never get 2 bullets in the boxes at the same time. Well, if the gun isn't going off too fast and I have enough time between things, you see, slow down the...
So again, he's trying to say, well, we're going to do the single photon experiment or the single electron experiment. We're not going to flood the device. We're not going to create any opportunity for bullets to hit bullets or any of that kind of stuff. So he's basically describing doing the experiment one quanta of energy at a time, one clump of energy at a time.
The gun, so they go off very slowly. Bing, 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 bing. Then put the 2 things here and look very quickly in the 2 boxes. You'll never get 2 bullets at the same time in the 2 boxes because the bullet is a single, identifiable lump. I call that characteristic of the object that it comes in lumps. So the first thing about bullets is that they come in lumps.
So again, sort of this is where the confusion starts. This is a sort of a really inexact statement in the sense that because of how we've identified a photon based on an energy profile, a total energy profile, we've sort of ignored the need for there to be a ray of light. And we know that happens with our own eyesight, that we need a certain number of elements of a photon that hit our retina for us to see that a photon happened. And you can make devices that have variable sensitivity, that need a certain amount of photonic energy to have an appropriate reaction that we can measure, and ones that can vary in how much energy they need to be hit with before they trigger an event that we can detect. So this kind of just messes it up because, yeah, there's a clumpiness to the ray, but there's inside the ray also clumps.
And now what I'm going to measure is how many bullets arrive here on the average in a long period of time. So you wait an hour and you count how many bullets are in the can, in the sand, and average that. Now, we call that, if you want, per, let's say we take a definite time like per hour and say the number of bullets that arrive per hour. And sometimes you could call that what's called the probability of arrival, because it just gives a chance that a bullet going through this thing arrives in this particular box, at least it's proportional to the chance. One way to measure is to measure the average number of bullets that arrive over a period of time.
Right, so you could simplify this by just saying as you change the position of the box, you give each box position 1 hour of time to collect bullets, and then you just count how many bullets each position collected.
Now the number of bullets that arrive in this box here will vary as I vary X. And I'm going to make a graph here in which I plot horizontally the number of bullets that I get if I hold this thing here for an hour. And I'll get a curve that will probably look more or less.
So he said that wrong, of course. And drawing this curve the way he draws this can lead to lots of confusion because he's now drawing a possible outcome and then another possible outcome and another possible outcome depending on how he changes circumstances. But obviously you would have to move the box to get the pattern for the entire picture. So this would have to be after many hours and many samples, and then you get this image. Now, I would argue this hasn't been done in terms of this expectation of where bullets would go. I think bullets would be a lot more precise than this, frankly. They wouldn't be doing this shape. They would have a very different shape. But anyway.
Like this. Because when the box is behind one of these holes, it gets a lot of bullets because ones that went through this hole, and otherwise it gets them that went through this hole. And if it's a little bit out of line, it doesn't get as many. They have to bounce a little off the edges of the hole, and so it disappears like this.
So let's understand. So what the real illusion is that the slits are not much bigger than the slit that produced the light. I mean, it's a tiny, tiny, tiny difference, and you're projecting the image at a great distance. And so the tiny difference of the bullets would almost turn the two slits into one slit, and those two humps, okay, would be way overlapped. So they would be much, much closer to each other, you know, like this knuckle difference. They'd have a tiny difference dependent on the distance between the two slits. So the distance would, that distance would stay consistent. And so those two humps should be riding on top of each other a lot more substantially. So again, it's just a subtle inaccuracy, but it's an inaccuracy, and it just shouldn't be there. This shouldn't be done sloppy and lazy if it's a foundational experiment for which they're justifying a bunch of theory about what the real causes of our reality are. This is our reality experiment. This is the God. This is the kernel of the thing. And if you can't treat this with a heightened precision, who knows how many later mistakes you're capable of.
And this is the number that we get in an hour when both holes are open. And I call that, by an abbreviation, N12, which merely means the number which arrives when hole number 1 and hole number 2 are both open. Looks like that, say. Now, I must insist that the number that we're plotting here doesn't come in lumps. It can have any size it wants. For example, there can be 2.5 bullets in an hour. In spite of the fact that the bullets come in lumps, what I mean by 2.5 bullets in an hour is that if you run a long time, like 10 hours, you get 25 bullets. So it's on the average 2.5 bullets. The N can have any size. It doesn't have to be in lumps because it's an average. I'm sure you're all familiar with the joke about the fact that the average family in the United States seems to have 2.5 children. It doesn't mean that there's a half a child in any family, whatever. The children come in lumps.
So, yeah, well, whatever. If I wasn't familiar with the joke, then okay, funny.
Nevertheless, when you take the average number per family, it can be any number whatsoever. And so this number N, which is the number that arrive in this container per hour on the average, need not be an integer. It can be a tenth, which would mean under those circumstances that you have to wait on the average 10 hours more or less per bullet. So what we measure then is the probability of arrival, which is the technical measure, the probability of arrival. It's a technical term, really.
Yeah, so it's just this is part of the engineering the conclusion. He already has a conclusion, so now he's going to use rhetoric that'll verify the appropriateness of the conclusion he's already drawn about what the cause of this is. So he could just say the number that arrive. He could call it lots of things. This throwing the word probability in is already now implying randomness or some unknown cause or undetectable cause, because that's mostly what we talk about when we talk about probabilities. You don't really talk about a probability when I don't know, there's two doors, that you could choose to go through. You obviously understand that there's reasons why you choose one door or the other door. You just don't magically pop through one door or pop through another door. there's causes to what door you go through.
The average number that arrive in a given length of time. And now finally, if we go to analyze this curve N12, we can interpret it very nicely. We can interpret it as the sum of two curves, which I will draw here. You see, that's why I need the blackboard, so I got several cases. So I draw two curves here. One which would represent what I call N1, the number which would come if hole number 2 is closed by another piece of armor plate in front, and so they all come through number 1. And N2 would be the number that comes through hole number 2 alone. So N1 is the number that comes through hole number 1 alone, and N2 is the number that comes through hole number 2 alone, those numbers being determined by closing the respective holes. And then we discover a very important law, which is that the number that arrive with both holes open is the number that arrive by coming through number 1 hole, plus the number that comes through number 2 hole. And
so again, making this some sort of important distinction is merely, and again, part of pre-knowing what their conclusion is about what's causing the effect. So this becomes something worth emphasizing when it seems kind of obvious that there's only 2 openings, the bullet has to go through one of them. Yes. Duh.
in this proposition, the fact that all you have to do is add these two together, I call nice, or no interference. That is, what you get from the 2 holes open is the same as you get by simply adding each hole separately. That's for bullets done. We're done with bullets.
Okay, no indication. Let's say if you had a, I don't know how you would detect it. I'm just trying to think. The implication being that the bullets are not behaving in any manner that indicates the bullets are hitting anything on their way. So whatever they come out of the slit going in that direction, that's the place the bucket they fall in. I mean, the results aren't going to change any if there is interference. You're still going to have the same number of bullets. So you can't change how many bullets get through whether there's interference or not. So in my opinion, that's a distinction that just can't mean anything, frankly.
I begin again. This time with water waves. Here is standing some kind of a big mass of stuff which is being shaken up and down. This is a long line of barges or jetties with a gap in the water in between. Perhaps instead of do with ripples, I mean, this to do with big ocean waves that sound more centralized. Wiggle my finger up and down here, and I have a little piece of wood here, and ripples start out here, and then I've arranged in a tank to put boards in the way here, so that I have these 2 holes, and then I have this so-called detector, and then what...
So now an important part of waves is that this is more stuff that they know, is that when they encounter surfaces, the water slows down. So especially bottom surfaces. So as the water, as an ocean gets less and less steep, deep, the ocean water, the reason why waves crash is because the bottom water is moving much slower than the top water. So the top water just moves ahead of it and crashes. It flies over the thing it's sitting on because it's going faster. So the opposite happens when you have the surfaces on the side, is it's sticky. The water sticks to the surfaces, moves slower. So the middle water is going faster, the side water is going slower, and that's what creates your rounded wave. Now, people who are trying to apply this to photons, where's the theory? How do you make it fit without saying, oh, there has to be some sort of interaction with the surfaces that somehow drags the photon to create a new kind of photon wave that's now round instead of flat. So they have to, in some sense, concede that slits are causing the effect, that the surface is causing the effect.
What I do with the detector, what the detector detects is how much the water is jiggling. For instance, I put a cork in the water and measure how it moves up and down. And what I'm going to measure, in fact, is the energy of the agitation of the cork, which is exactly proportional to the energy carried by the waves.
So, but there should be a recognition that this is measuring something completely different in the sense that it's not a bullet, all right? It's something that's too high and then something that's too low. So there's a bunch of pressure and then there's no negative pressure. There's a pull and a push. No such thing as a pull, but there's positive and negative pressure, an extreme, and then there's a neutral, something that just stays one way, and the other thing goes plus and minus to that one way. That's probably the better way to say it. So it's all positive push, you could argue, and the difference is that the one thing is going positive and negative, and the other thing just stays neutral between the two pressures. So the off wave has a 5, the on wave goes from 10 to 0.
Also, I forgot to say that this jiggling is made very regular and perfect, so that the waves are all of the same spacing from one another, and then I will describe what we get under those circumstances. For that, I first remark, well, let's see.
See, just as he described it, the distance between this first slit and these secondary slits, the thing he just pointed out is he's getting round waves now, so he's sending round waves to the two slits. Now the only thing that doesn't matter is the fact that the slits are so close together that there won't be much phase difference in the waves, because you're not going to pick up as much of the roundness. You're close enough to the flat top, so to speak, of the wave that it won't matter much.
First, we can measure the energy of the core, but then another thing is important for light. I call it water waves, water waves, is that the thing that we're measuring can have any size at all. We're measuring the intensity of the waves, or the energy in the core, and if the waves are very...
See, that's the trick, though, is that's not what you would measure. You would just measure the difference between the wave that's on and off, and it doesn't really matter whether it's doing this or whether it's doing this. You're just measuring that there's a spot that has complete calm and there's a spot that's jiggling. So when you're measuring it, you're just going to be measuring wave action, no wave action, wave action, no wave action. So in a sense, it still comes as clumps, even though I agree with why he's saying this. So this is, again, more of the preconceived notions going in, his personal axioms polluting the conversation, in the sense that he doesn't really think it's waves, and so he's going to sort of kind of indicate how waves don't wake because they're not clumpy enough.
Quiet. If the fellow over here is only jiggling a little bit, then there'll be very little motion of the core, and so on. No matter how much it is, it's proportional. So it can have any size. It doesn't come in lumps. It's not all there or nothing. And what we're going to measure is the intensity of the waves, which, to be precise if you want, is the energy generated by the waves at a point.
Well, that wasn't very precise. What he's measuring is the difference between no wave action and wave action. That's it. So he's basically just measuring, is it nothing, no action, or action. That's it.
And now what happens if we measure the intensity, which I'll draw on a third curve here, which I'll call I to remind you it's an intensity and not a number of particles of any kind, and I12, when both holes are open, is a curve that looks something like this. Another interesting, complicated looking curve, which ought to be symmetrical. Didn't do too badly, actually.
All right, so this is, again, just, you know, if you're really not gonna do it the way it's supposed to accurately, then why do it at all? Can be the argument. Clearly, what's seen in photons is numerous bars of relatively equal intensity, substantially even looking, until you start getting pretty peripheral, and equidistant, and depending on what kind of light source, they can be round circles or they can be rectangles. They can be lots of different things. Again, by the description of how he did this with two holes, this pattern would be a ring pattern. But anyway, and what he didn't include was the fact that in the double slit there are actually two patterns. There's this lumpy stuff, and then there's a little dead space, and then some more lumpy stuff, and then dead space and a little more lumpy stuff. You know, that it fits inside of an envelope of a lump. Okay, of a divergence. And so the real experiment doesn't produce this pattern in photons, but he'll keep going back to this pattern created by water waves. So the water waves do this. They don't create two patterns. The photons and the electrons, well, the photons definitely create the two patterns.
Very complicated looking curve. That is, if we put the thing in different places, we get a very, very different intensity, which varies very rapidly in a peculiar manner. And you're probably all familiar with the reason for that. The reason is that the ripples, as they come out of here, have crests and troughs spreading from here. And they have crests and troughs spreading from here. Now, if we're at a place which, say, is exactly in between these two things, so that the two waves arrive at the same time, the crests will come on top of each other, and there'll be plenty of jiggling.
So it's just talking about how there's interference when objects have a phase, a frequency, and they are traveling different distances. So this distance is longer than this distance. The phase can't possibly be the same, even though it started off the same. It can't finish the same. And where they're on phase, they multiply. When they're off phase, they destructively become a neutral. So it's not a complex effect, and it creates a simple on-off pattern. But there's lots of other ways to create an on-off pattern. I can just spin a wheel with a flashlight on it, and flashlight will blink, 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 on-off.
Which is the exact opposite of this curve. So I'll have to put, there should be another bump. We have a lot of jiggling right in dead center.
Well, this is hardly dead center. This is way off center. The slits are this way, and now he's put this middle line below, so it's not that good a drawing, actually. But whatever. Minor detail.
On the other hand, if I were to move to some point here, since I'm further from hole 2 than hole 1, it takes a little longer for the waves to come from 2 than from 1. And when 1 has a crest arriving, the crest hasn't quite reached there yet. All
right, so again, he did draw, this first pattern so wrongly, okay, that now we're stuck with this wrong impression about how close these two things would be to each other, and they would be very close to each other. They'd be overlapping, and just a tiny difference at their peaks.
2, in fact, it's a trough from 2. So the water tries to move up, and it tries to move down from the influences of the waves coming from the two holes, and the net result is it doesn't move at all, or practically not at all, and so we have...
Right, but we know from energy conservation that the energy went somewhere, though. They both had energy. They lost their energy. They did lose it, and they lost it to something. So the energy went somewhere.
Have these low bumps at that place. And then if you move still further over, you get enough delay that when a crest is here, this other crest is in fact one whole wave behind. So in fact, it's a crest that is two crests are coming on top of each other, but not the same crest, so to speak. The fourth crest from here and the fifth crest from there on top. So you get a big one again and a small one, a big one, small one, depending upon the way the crests and troughs.
Should be saying something, nothing, something, nothing would be a better way to say it, but fine.
Interfere, as we say. The word interference, again, is used in science in a funny way because we'll have what we call constructive interference. When they both interfere here, it makes it stronger. Well, they call it interference anyway, but the very important thing is that I12 is not the same as I1 plus I2, and we say it shows interference. Yes, interference. That's a funny term we use it. Constructive and destructive interference. I didn't mention what I1 and I2 look like, but we can find out by closing this, for instance, to find I1.
So he's saying it just because it doesn't come out in these two clumps, therefore it doesn't equal. Well, it equals in the sense that it's just as much energy, it's just in a different form. On, off, on, off.
The intensity that you get here, if the hole is closed, is simply the wave from one hole for which there's no interference, and that's this curve. N1 is the same as I1, and the same way otherwise I2, and this curve is quite different than the sum of these two. As a matter of fact,
so he's just pointing out in water waves, if you block one of the slits, you just get the clump. But we already know from Newton that with photons, that rule isn't consistent. So you can't use this analogy and be fair, because we already know from Newton, 1650, that that's not how it works. The single opening has these surfaces, and there will be, in photons, pattern created. There will be an interference pattern. I'll use the words interference pattern. I don't, not to say that it's interference that's causing it, though. It's the same pattern, on-off.
Mathematics of this curve is rather an interesting one. What is true is this, that the height of the water when both holes are open is equal to the height that you would get from number 1 open plus the height that you get from number 2 open. Thus, if it's a trough, the height from 2 is negative and cancels out the height from 1. So you can represent it by talking about the height of the water. But
so in a sense, he's might be saying or suggesting that the energy is conserved. So where there's destructive interference, the energy of that interference is the thing that's causing the greater amplification of the constructive interference. That's where the energy for it comes from.
It turns out that the intensity in any case, for instance when both holes are open, is not the same as the height, but it's proportional to the square of the height. And it's because of this fact that we're dealing with the squares that we get these very interesting curves. All right, now, we erase the machinery.
So all it's saying again is that when you square it, you're just talking about area. So you take the area of all the positive lumps as area, and they'll be the same as the two lumps in terms of the amount of area. So that's all the squaring is just saying, is you're taking the area displaced by the two events and measuring the area as a measurement of the intensity.
And start over. This time we start with electrons. We have a filament here, tungsten plate, holes in the tungsten plate, and for a detector, any electrical system was sufficiently sensitive to pick up the charge of an electron arriving with whatever energy the source had. Or if you would prefer, we could use photons, and this is the black paper with a hole in it, 2 holes in another sheet of black paper. Paper isn't very good because the fibers don't make a sharp hole. We use something better.
I love the way he just edits himself. But yeah, you know, paper doesn't make a great surface. There's a whole lot of surfaces, a lot of hairs on the surface.
And here, for a detector, a photomultiplier that can detect the individual photons arriving. Now, what happens with either case, and I'll discuss only the electron case, the other case is exactly the same, the case with photons.
So again, it's not exactly the same, so this is again just, you know, the truth is, if you look at the patterns, they're quite different. The electrons create a very gradual on and off pattern, very smooth. The intensity has a little tiny bright line in the middle, you know, and then it goes all the way to dark, and then it goes all the way back up to bright, all the way down. So you're getting a, you know, you're getting a really clear sinusoidal pattern in terms of the intensity. Photons on, off, much less gradation, much less rounding is apparent. Very little roundness is apparent. So they're not exactly the same. And again, I'd say that is clearly understandable if you think in terms of the mechanics. Electrons are big, photons are small. Okay, so use this finger. When a photon interacts with an electron, okay, it has a very specific reaction dependent on the electron. It's going to be a pretty solid reflection at any one angle, where two electrons, when they interact, they have force, charge. The charge is repulsive, and they bounce off of each other's force. And so that's much smoother because they're bouncing off a bigger curve because they're bouncing off charge.
First, and what we receive in this electrical detector with a sufficiently powerful amplifier behind it are clicks. Click, 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 and so on with the source here.
But that's the same thing our eye is doing. Click, 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 like a screen. It says pixel, 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 pixel. But we know our eye is only detecting photons of a certain intensity, a certain amount of photons. So we're not doing the clicking thing for lots of the energy. Lots of the energy, we're missing it because there wasn't enough in the stream to click our clicker. So this is a little nuanced. And it's not as simple as just saying it's a clump. Well, yeah, that's the only way we can see it. We can only see it when it's a clump. There could be non-clump, insufficient clump, too small a clump.
Lumps. Absolutely lumps. When the click comes at a certain size, and the size is the same, if you turn the source weaker, the clicks come further apart, but it's the same size click. You turn it up, they go quicker, quicker, and it jams the amplifier. So you have to turn it down enough that there aren't too many.
So I'm just saying there is some physics here that's a little bit more complicated. So I'd almost argue that, yeah, you can say this, but you should qualify it by saying, you know, it's kind of a complex theory here, because we can make a photomultiplier that's much more sensitive, so it needs a smaller and smaller amount of clump. But as we do that, then it starts picking up all kinds of noise from the environment, which would be an indication that the environment is full of these little pieces of energy that we're not seeing, but the photomultiplier can see it. And so this, like I said, this is a subject that you just can't make, you can't make these kind of, this is the way it is, statements, when the way it really is a little more complicated.
Clicks for the machinery that you're using to detect. Next, if you were to put up another detector here and listen to both of them, you never get two clicks at the same time, at least if the source is weak enough so that, because of the precision with which you measure at the same time. If you cut down the intensity of the source so they come few and far between, they never come a click in both detectors. So that means that the thing which is...
So again, this is one version of doing the experiment, trying to send in energy at such a slow rate that you can call it one piece of energy at a time. But all of those experiments, you know, I haven't seen them ever done the original way with photographic paper in any modern experiment. And what I have seen is attempts to use technology, and the pattern is not as good. It's very noisy. 50% of the signal is noise, which is a really high percentage compared to when you do it visually. The difference between the light and the dark is pretty clear. It's not like, you know, there's just a clear distinction.
Comes in lumps. It has a definite size and it only comes to one place at a time. All right, so for electrons, or for photons, what is this you doing?
Yeah, well, we know an electron is a clump, so that's an easy one. So we probably should stick to that if we want to stick to clump theory. But again, there's reasons why that's not convenient either, because then obviously you're using something that's charged, and then the question becomes, well, wouldn't we have an expectation that an electron would, because it does have charge, that it would be reacting to a surface, because the surface is going to be either plus or minus. It's going to have pluses and minuses in it, and it's certainly going to wobble the electron and cause it to go in or cause it to go out, and maybe it's going to cause it to do a few things before the electron finally leaves. But it would certainly have the potential to affect the direction of the electron, and that would be perfectly reasonable to expect an electron not to be very comfortable traveling next to a surface because the electron is charged.
It comes in lumps.
In other words, I mean, charge, I can say the word charge and you have an understanding, Feynman had an understanding. To me, the best to understand charge is it means it's lit, okay? It has a force. It's emitting a force, a repulsive force to other electrons. So you can think of it as a positive thing. It's expelling little bits of sand or whatever you want to call it. And the source of the sand comes from the environment and it's shooting it back out, but it shoots it out in a specific way that means it's negatively charged. Takes in one thing, something else leaves. It reflects. So you see, this is where it gets complicated. But I'm just saying, to understand what charge means, you have to think of it as it's like a sun. It's radiating an energy, and that energy is going to push things away from it. That doesn't even. I mean, that's a very incomplete because we're positive and negative charge. So I won't do my theory on this video, but it is understandable that there's two kinds of force.
And therefore, what we can do is the same thing as we did with the bullets. We measure how many come, we measure the probability of arrival. What we do is we hold the detector in a certain place. Actually, if we wanted to, although it's expensive, we could put detectors all over at the same time and make the whole curve simultaneous.
Yeah, we could put photographic film. I mean, it really isn't that expensive, and it just isn't done very often. That's why they won't have pictures of it done that way. But it really is the way it should be done.
But let's suppose we put it in a certain place and we measure at the end of an hour how many electrons came, and we average it. By the way, if I put detectors all along the back here, when one comes, it comes into one, but not from others. Because one goes off, and the other goes off, and this goes off, and that one goes off. Just like the bullet.
Just like a straight line force. So, he's just trying to emphasize the point that wherever it gets hit because it didn't go two places at once. It didn't spread like a wave. So again, he's sort of making the non-wave explanation. And because he doesn't believe it's a wave, he's decided it can't be a particle for whatever reason. And so he's just going to say it's random. That is, that whatever goes in somehow is randomized by some random machine. It's not even a machine. It's just the universe says, Heisenberg, I like Heisenberg. The universe says, I like Heisenberg. I'm going to accept his theory, and I'm just going to screw this up for no good reason. I'm just going to pretend it can't possibly do this, so I'm going to randomize its outcome. When I think if you're a reasonable person, you're saying that's not cause and effect. That's not the universe. Everything in this big universe is so mechanical, so I'm so obligated to charge a battery before I get energy out of it. I'm obligated to learn how to speak English. I can't just automatically do it. I mean, all this stuff, there's no breaking of cause and effect in our real world. Why do we think it breaks in this world? It's just such a dangerous thing for them to establish as a fact.
We measure then the probability of arrival of the electrons. And what do we get? The number of electrons that arrive. The same kind of an N12 as before. This is what we get for N12.
So we think that's a punchline. It wasn't much of one. But anyway, well, we're halfway through, so yeah, sorry, this is a long video, but again, these subjects are, it's just important, and this conversation just doesn't take place in professional physics. They don't go back to any of this stuff and reanalyze it and say, where is it possible we made a mistake somewhere in these conclusions? Maybe this wave-particle duality stuff is nonsense. Maybe we can figure out why there's this change in the effect, depending on what we put in as causes. And there's just no will to do that. They're satisfied with the evidence they jumped. They're satisfied with the position they have, and I would argue that it's such an ugly place to be. Why would you want to stay there? I mean, ugly in terms of logic and reason. I guess I'm back. Yep. It looks like it anyway. All right, continuing. Mostly.
And 1, 2. This is what we get with both holes open. And that's the phenomenon of nature. That she produces the curve, which is the same as you would get from an interference of waves. But
so anyway, it's just kind of a simple thing, right? So all this N1, all this, we're starting to use symbolic jargon, which probably isn't necessary at this stage of describing a crime scene. There's a crime. There's somehow stuff that we know goes straight, was going straight, and somehow it's not coming out straight. And we're just saying, okay, what's the cause? And in my opinion, it's just the wrong answer to say the cause is something silly or crazy. The cause is something simple and mechanical. You just have to find it.
She produces a curve for what? Not for the energy in a wave, but for the probability of arrival of one of these lumps. The mathematics is simple. You change I to N, and you have to change H to something else, which is new. You call it something because it's not the height of anything, but in order this curve as a simple mathematical form. There's an A, which can be represented as an A1 plus an A2.
Right. Well, so again, this mathematical form gets kind of messy because this is part of their, again, part of the game played is that they come up with a formalization for a very simple pattern. So you come up with a formula that explains basically the phase geometry. It has built into it the assumption of the phase geometry. It doesn't have the geometry in the equation. It has the product of the geometry in the equation. And it's just represented by variables that control that geometry. And so we know the variable is the frequency of the light in the light experiment changes where the waves will end up interfering. Same way with water waves. And the other variable is the width of the slit in the single slit. Now when they do the double slit, they change that variable, the width of the opening, to the width of the impediment. Now I would argue that only works as if the surfaces are causing the phenomenon, because then you've kept the same number of surfaces, you have surface. So that makes sense, that the surfaces are still in the same place. You've just changed whether it's a brick wall or an opening in a brick wall. But the two surfaces would be in the same location. So then the maths can make sense. But by their theory, why the switch is fundamental. It's a fundamental difference. In one experiment you're measuring how wide the slit is, and in the next experiment you're measuring how thick the impediment is, which means you have to assume the width of the slits. So their math is completely vulnerable to you changing the width of the slits in the double slit, and the math won't account for it. The math doesn't have any variable for that, because you use the variable for the brick wall in the way. So the math isn't at all perfect. They have to force it to fit.
Which we call a probability amplitude, because we don't know what it means. Which to arrive from hole 1 plus the probability amplitude to arrive from hole 2. And you add the two together to get the total probability amplitude to arrive and square it. Just direct imitation of what happens with the waves, because we've got to get the same curve out, so we use the same method.
So again, they're just saying that we know the intensity is measured by this way of drawing it. This way of drawing the intensity, your intensity will be captured in the area underneath your curved line. So everything on this side of the line, okay, is going to be the area that represents having something arrive. And so that's all they're doing. They're just saying this, the way they're drawing it, area works as a way of representing intensity, because everything on one side will be on and the other side's off. No, nothing and something.
Mathematics. Let's find out. I better check on one point, though, about the interference. I forgot to say, what happens if we close one of the holes? Let's try to analyze this interesting curve, which now, for electrons, I erase all the stuff with the light. Well, everything with light is erased. And now we're talking about electrons. This curve isn't important in our case. This is the number which arrives. Now, we would like to analyze this curve. And we try this. We say maybe it comes, we can analyze this by thinking the electrons come through this hole or through the other. So we can close one hole and measure how many come through hole number one, and we get that curve. Or we can
So again, he's using these drawings from the bullet example or whatever example where he's got the two curves so far apart. The two curves would be right on top of each other, just a tiny bit of difference between the two. Because the only difference is the tiny distance between the slits, which is tiny relative to the screen. It's like the difference between a movie projector and the movie screen. Huge difference in sizes. And if I had two projectors show the same movie from 10 inches apart, you're not going to see that difference on the huge screen.
close this hole and measure how many come through hole number two, and we get that curve. And these two added together is not this, and so this is not the same as N1 plus N2, and it does show interference. It shows interference.
Well, like I said, they don't have any evidence of these because they've never really done these intensity experiments to measure exactly if it is equal. Like if you open one slit and measure how many photons, just total amount of energy gets through, and then you open the other slit and total amount of energy, and then put the two open, total amount of energy received in the sense of you detected. There could be a difference in what you're detecting. Just saying, they haven't really done the experiments with any precision, so we really don't know the answers to these questions with any precision, because the experiments just don't exist.
And in fact, the mathematics is given by this funny formula.
Not at all that I'm arguing there would be any difference. I'm just saying that when he says not equal, it is equal. I mean, there's no reason to think any photons are lost somewhere by changing it from a one slit to a two slit. You know that with two slits of the same size, you have twice as many photons as you have with one slit of the same size. There's no reason to think that's wrong, but I'm just saying they've done nothing to verify it. There is no real evidence that it's true.
The probability of arrival is the square of an amplitude, which itself is the sum of two pieces.
So when he says a square of an amplitude, again, all he's doing is saying, look, this is the way I like to measure things. I don't like to make bar graphs. I like to do, or yeah, he likes to do bar graphs, where you could do a radial graph, or you could do some other graph that doesn't have to do with area, length of a single line or something. And so just because of the way he likes to visualize it, area is important, but area isn't. You don't have to go by the area. You can just go by the raw intensity. So as long as you don't square one number, you don't have to square the rest of the numbers. The proportionality still exists without squaring it. It's just if you're going to make it into a bar graph, then area becomes important.
Now the question is, how can that come about? That when they go through hole one, they would be distributed this way. When they go through hole two, they would be distributed that way. How can it be that when both holes are open, you don't get the sum of the two?
So again, the first argument would be you don't get those lumps. So this is the photon problem. So this is directly, he just said something that just isn't true. So let's replay it, because Newton says this isn't what happened. Newton already discovered this. So this is a 350-year-old mistake. I don't know how to, I mean, it's a very big mistake in terms of describing what really happens with photons and electrons.
So we can close one hole and measure how many come through hole number one, and we get that curve.
That's not what you get. So when you have a single small aperture, you get a pattern, interference pattern. You get bars. And they were called Newton's rings 350 years ago, after Newton. So it's a phenomenon already known. If I make this hole smaller and smaller and smaller, the pattern gets bigger and bigger and bigger, and that is, it's stretched. So the bars that were this thick, you get to be this thick, and then this thick, and it just thickens everything. That's all that happens, but that's the reality. There is no, in photons, there is no, it's just a clump. There's just a wave. There's just a round wave. The single slit doesn't create just a nice little round wave. There's no clump. There's no just a hump. There's a pattern. Newton's rings.
Or we can close this hole and measure how many come through hole number two, and we get that curve.
All right, so it's just wrong to say that. You can't do an experiment that makes that happen. I've tried. You can't make just a clump. It's the bars are always there. They're just spreading wider and wider.
And these two added together is not this, and so this is not the same as N1 plus N2, and it does show interference. It shows interference, and in fact the mathematics is given by this funny formula.
All right, so we're stuck with this idea that this is always interference. It shows interference. That is, there's an on-off pattern, which all it's saying is that there's a clump, a quanta of bending of the light. The light bends in certain clumpy amounts. It bends 3 degrees, or it bends 6 degrees, or it bends 9 degrees, or it bends 12 degrees. So it's always in clumps of an amount of bending. It doesn't bend 2.5 degrees, or 1.5 degrees, or some other incremental amount. It always bends by a specific degree amount. And that's all. That's all the facts say. It doesn't say interference is a fact. That's their projection of a cause. And that was the mistake, was to jump to a conclusion before you've proven the conclusion.
That the probability of arrival is the square of an amplitude which itself is the sum of two pieces. Now nobody, the question is, how can that come about? That when they go through hole 1, they would be distributed this way. When they go through hole 2, they would...
So he's just saying it again, wrong, just wrong. You know, what else can you say? It's wrong. It's an elemental experiment. Their entire physics is based on it, and they don't describe it correctly. I mean, that's wrong.
It would be distributed that way. How can it be that when both holes are open, you don't get the sum of the two? Instant. If I hold it in...
Yes, you don't get the sum of the two in the sense that the pattern doesn't just create the same pattern superimposed. So something changes. But my argument would be is we already know something changes. We know that when you make the slit smaller, you create more likelihood of further, deflections. That is, instead of 3 degrees, it does do the 29 degrees instead, or 48 degrees, or 96 degrees. So you increase the likelihood of a wider angle change. So we know moving the slits in proximity to each other changes the pattern. That is, whether I make the impediment smaller and wider, I changed how big an angle the deflection is. So we know that there's a relationship between the two slits. Somehow they're connected to each other. Somehow it matters how close they are to each other. It is going to change the pattern. So we know there's some sort of information, some sort of connection between the surfaces and their proximity to each other. The closer they are, they do something different. The same frequency light goes in, and yet you get more bending. Clearly. All right? So we already know there's a connection somehow. And they're physicists, and it seems to me they can't figure out that the connection is that atoms communicate energy. Surfaces charge at different rates. If one surface goes minus, the other surface will likely go plus. These are the rules of atomic structure, and yet they don't consider anything to do with the matter. The matter is irrelevant to the subject, and the only thing they care about is photons must be doing it. Photons are deciding to go more or less, and it doesn't have anything to do with the surfaces. And I'm just saying you can sort of understand that, well, this should have been teased out some more. There should have been some conversation where you demonstrated how the surfaces have no effect. When clearly, if you're a physicist, you'd understand that the surfaces are going to be changed by proximity.
At this point here, I get practically nothing. If I close one of the holes, I get plenty. If I close the other hole, I get something. If I leave both holes open...
Right, so the two atomic structures have, like I said, the closer I bring the two surfaces to each other, the change is what the electrons are doing on the surface of the protons, and it'll change how the light's deflected. So if I add surfaces, then I'm going to change the where the light's going to end up going. Even if the light doesn't go to one of those other surfaces, even if it's going through the same slit, of course this slit changes when there's another two slits over here, because this slit's going to know there's another slit over there. It's going to know there's another surface. It's going to be affected by the other surface. And the other surface is going to change the electrodynamics of the entire material inside the circle of the influence. So of course you would expect a place that had light doesn't have light, because now you've changed how much the light's being deflected.
I get nothing. If I let them go through both holes, I don't come anymore. Or take the point in the center. You can show that that's higher than the sum than there was in the other case, than the sum of these two. I get more here.
See, well, the sum of these two is they're drawn in the wrong position. So again, that's not accurate either. It is equal to the sum. If you actually drew these two things on top of each other the way that actually happens, it would be equal to the sum. I mean, extracting the fact that you have put a brick wall between the slits. I mean, obviously, obviously you're killing the most intense light when you put a brick wall in front of the middle. So you have to do your measurements with understanding that you do close one surface and you have the other slit off center to be able to do it. I mean, if you put the single slit in the middle and then you do the double slit with the slits this way, obviously those comparisons are going to be different because the light over here is less intense than the light right here in the middle, obviously.
When both holes are open, then I would get with either one of the two closed. Now you might think that if you were clever enough, you could argue that they have some way of going around through the holes back and forth, and they do something complicated.
Yeah, no, I wouldn't think anything like that. No, that wouldn't be my first choice, is to think the photons reverse and swing around and do all that stuff, because there's absolutely no reason to think photons can do that ever. So that would not be my first choice as an explanation. My first choice as an explanation would say matter's got a bunch of complex crap going on, and surfaces of matter, we already know the surface is a weird thing. One surface is a perfect mirror, one surface is perfectly opaque and absorbs all the energy. The surfaces are incredibly interesting places, and that's the first thing I'm going to think about. What's the surfaces doing? How are the surfaces affecting this experiment? And they don't care.
It splits in half and goes through the two holes and so forth in order to explain this phenomenon. Nobody, however, has succeeded to get.
Okay, so I mean, I love when they say something like nobody did something when nobody they respect or nobody they care to listen to. All right, because I could argue that back in Newton's day, there was a guy called Fadio. I can't remember his first name, but anyway, and he had a particle theory of gravity, and it perfectly diagrams gravity. It's now called Mach gravity, and had one or two little tiny flaws that could have been fixed by anybody with a little bit of imagination. And Newton liked it for 10 years and then decided in the end, now it can't work for whatever reason Newton decided. And maybe it was just political because Fadio was a bit of a loose cannon, weird religion that Newton didn't like. But anyway, it's always politics, right? It's really lousy that it just ruins everything. But anyway, how we have to identify and then become enemies. This is just getting my brain going on that subject, which I want to get back to where I was. So anyway, Fadio. So there could be theories, could be explanations, and he's saying nobody, but who knows? It could have been a guy 50 years ago, could have been a guy 100 years ago. And it's just, these guys just couldn't care less. They have their agenda, and their agenda isn't, hey, bring your ideas in, let's take a look. Because maybe there was one that had a kernel of, that could possibly work. All we got to do is fix this thermodynamic problem or this. Maybe that could, they don't do any of that. So his statement that nobody's done anything, it just means that nobody in our group has done anything. So our group of 500 people, let's say, that group didn't do anything. So therefore the whole human race didn't do anything. And I think that's sort of probably bullshit.
an explanation of this that's satisfactory, because the mathematics in the end is so very simple. The curve is so very simple.
Yes, it's just phase differences. It's just geometry, and it's just that simple in terms of how the pattern lines up. It's just a 3 degrees, 6 degrees, 9 degrees, 12 degrees. Not complicated. Not a complex event is happening. The cause isn't dramatic. It's just 3 degrees, 6 degrees, 9. It's just a multiple of a amount of bending. It's just a push of the same magnitude.
I will summarize then by saying that electrons arrive in lumps, like particles. But the probability of arrival of these lumps is determined like the intensity of waves would be.
Okay, but it's not in the single slit, and it's not in the multi-slit. So they don't fit the wave pattern in the multiple slits and in the single slit. So when he says it's not really like. And then even in the double slit, the photons create 2 patterns, not 1 pattern that the waves would create. So we have a mystery still. We have an effect that's more different than the wave effect, and therefore it doesn't really fit waves. And I could get into the whole arguments about how it doesn't fit the math because it's not gradually on and off in photons, lots of other things. Not matching perfectly at all. It's a very thin, weak, foggy match. Little bit looks like. Not a lot looks like. A little bit looks like. And they've just jumped. That little piece of evidence has given them license to say, we're going to call it interference. We're going to say it's doing what waves do. And there's no reason to jump. No good reason.
And it is in this sense that the electron behaves, as you might say, sometimes like a particle and sometimes like a wave. It behaves in 2 different ways at the same time. And that's all there is to say.
Yeah, see, then that's not all there is to say. So I think it would be silly to think it's not something pretty substantially like a wave or something pretty substantially like a particle. It's one or the other. It's not both. And clearly, you can understand particles can be at a frequency which makes them like a wave in the sense that they're a clump at a distance. So clearly they can do that. Waves, on the other hand, can't do clump. We don't have any physical examples of waves that don't spread, waves that aren't in a medium that loses, that absorbs energy by pulling on tension, stretching things that are in tension, so that the energy is dissipated and lost. You can't really make something that can travel billions of light years through space out of a wave in a medium, because the amount of energy from its perturbation, that is, its spreading, it would be an insane losses in terms of the energy it would lose over distance. And so wave really doesn't fit a photon at all, mechanically. You have to have some other word if you're going to use this idea of a wave that's like my finger and goes in a straight line. A laser wave, And aren't you really then just turning it into a torpedo? And once you've turned it into a torpedo, can't you just turn it into bullets? I mean, come on. I'm just saying this is the foundation of their mysterious, complex, mathematically engineered, hugely blah blah blah. You have to go to 10 years worth of physics classes to learn how to do the math of this complex blah blah, and all of it's based on this. Come on, this is ridiculous. These assumptions. This idea that, well, we've concluded it must be wavicles, or whatever the part was, some sort of mixture of the two.
I give a mathematical description to figure out the probability of arrival of electrons under any circumstances and so on, and that would, in principle, be the end of the lecture, except...
Yeah, so he would like to just simplify it. Just say, well, let's forget about thinking about causes and effects, and let's just have fun. Now that we know there's a pattern and it happens in a reliable way, let's have fun spinning the roulette wheel and trying to guess which hole it falls in, even though there's no point in it because we can't do the guess. But whatever. So he just wants to gamble. He doesn't want to think about it anymore, about causes and effects and how many surfaces the dice bounced off of or what happened. He's just saying, let's just assume the dice are going to do something magical, and we just won't worry about throwing the dice a special way or spinning them or doing something to try to influence the dice. Let's just have fun gambling in an ignorant way.
That there are a number of subtleties involved in the fact that nature works this way. There's a number of peculiar things. And I would like to discuss those peculiarities because they make...
See, well, he didn't bring up the major ones. The double slit having two patterns. He's not going to mention that. No, you know, it's pretty important. The fact that the single slit does create an interference pattern, that is, without two waves, without a source of two waves, it creates an interference pattern. Doesn't make much sense. These are the peculiarities that are important, and he's not going to pay any attention to those at all. The third one would be when we create a grid of these slits, a bunch of them, 1,000 of them, very close together, that we end up projecting images to locations. Clear, perfect images of the whatever you shoot at the surface, you'll get an image of it in different locations. Another peculiarity that doesn't fit wave theory.
It may not be self-evident at this point. So to discuss the subtleties, we begin by discussing a proposition which we would have thought...
I know I'm being so pedantic, or whatever the word would be. You know, you draw such a little space for this, the technicalities, you know, just a little space up here for the real stuff.
To use, since these things are low. Since what comes is always one complete, which I'll call an electron, one complete lump, one complete electron. It's obvious that it's reasonable that either an electron...
Yeah, it's kind of silly to say that an electron is a wave, and again, they did this whole de Broglie thing, so he has to put this in the context of where they've already done this, where they've basically already pretended electrons have a wavelength when they don't. They have a momentum. I mean, lots of cheats, and so he's calling this, like, this is being the real physics, and it's going to start off with a fake notion that somehow it's okay to think about, you know, a car going 70 miles an hour as having a 45-foot wavelength.
Electron arrives, or goes, let's say, that either an electron goes through hole number 1, or it goes through hole number 2. That seems like it goes through hole number 2. That seems very obvious that it can't do anything else if it's a lump.
Right, but they're pretending that it must be doing something else because something has to be interfering with it. And so it has to interfere with itself. If single electrons are put through the experiment, we have to come up with some reason that there's now two waves that can interfere with each other. And so they try to turn something quite solid into something not solid. And why are they contriving all this when that's evidence that the theory doesn't work? I mean, clearly when I have to turn a car into two cars, you know, to have it do what it's supposed to do, I mean, it's completely nonsensical for somebody to say, no, my car turned into two cars when I turned around the curve, and it, you know, one car went into the ocean and one car, you know, went the other way, and then the two cars communicated with each other, and then the car landed in the average place. What? If somebody suggested that as an explanation for how a car got somewhere, I think everybody'd say that doesn't, you know, I don't think there's much chance that's the right answer.
I'm going to discuss this proposition, so I have to give it a name. I call it Proposition A. Now, we've already discussed a little bit what happened with Proposition A. If it were true that an electron either goes through hole number 1 or it goes through hole number 2, then the total number which arrives here would have to be analyzable as a sum of two contributions. The total number which arrives...
It's kind of a curious thing. I know this is just a pointless remark, but you know, people were kind of ugly in the 60s. And they got very pretty in the 70s and 80s, and then they got ugly again. Just noticing.
Idea will be the number that come here be a whole 1 plus the number that comes be a whole 2. And since this curve cannot easily be analyzed as a sum of 2 pieces in such a nice manner, and since the experiment which determined how many would have arisen would have arrived, if only hole number 1 were open, don't give the result that this number is the sum of these 2, it is obvious that we should conclude that this proposition is false. It is not true that the electron either comes through hole number 1 or hole number 2. Maybe it divides itself in half temporarily and so on.
Yeah, and so on. Maybe it does this, maybe it does that, maybe we create a new universe, maybe it hit a piece of dark matter. I mean, it's just so empty as an explanation in terms of if that's what a detective would do, is say, I can't, I think the Invisible Man did it, frankly. There's no other real explanation. It had to be an invisible man that did it. I mean, if he did that in court, who could take that seriously? And yet these guys are getting away with it. Because they're saying, I went to school for a very long time, I can do very complex math, I can do lots of stuff you can't do, therefore I know the truth, and I'm really good at finding truth. Now these are lousy detectives in my opinion. They're lousy, because they jump way past their evidence. They keep thinking, it looks a little tiny bit like, and then they just say, okay, it must be the same thing. I could look at the skin sample of a rhinoceros and the skin sample from an elephant, and I'll say, oh, look, it looks awful lot alike. Okay, elephants are rhinoceroses. No, that wouldn't be good science.
So proposition A is false. That's logic. Unfortunately, or otherwise, we can test logic by experiment. And so we just have to...
It's like a platypus, right? I mean, a platypus has a duck bill. It just really does. Looks very much like a duck. Has absolutely no relationship to birds at all. Nothing. Just happens to be that the duck bill idea, the bill, as a feeding device for algae and, small stuff, works. And so that's why it has one. It's because it works. I mean, kangaroos look a little bit like tyrannosauruses, little tiny... They're not related to tyrannosauruses.
To find out whether it's true or not that the electrons come through hole 1 and hole 2, or maybe they go around through both holes and they split up and go. We don't have to do. All we have to do is watch them. We watch them, we need light. So we put back here behind the hole a source of light, very intense light.
So he says intense in one minute, then he'll talk about how he has to reduce it because he's going to affect things too much. So anyway, so this is just a thought experiment. Again, this hasn't been done, this wasn't done. He'll even say in a sense that it wasn't done, but he doesn't say it directly, which is sort of irritating. So I'll get to that part later, I guess, just because this whole part gets quite convoluted when he starts talking about his detecting experiment, which never really took place, which never has been done, and which they should at least try, in a sense, because there's some hope that they'd get some of the pattern would still be retained, and they would be able to tell which slit it went through. I think it's a fact that they will get enough pattern will be preserved that they'll be able to see that the pattern is preserved to some extent. Maybe it's only 10% of the noise, but it would still be there, still detectable as a pattern. And but they've never done the experiment. They're just assuming that it can't be done because they have a principle from Heisenberg that says the small universe isn't hard to see because it's small. He says it's hard to see because it has different rules that are all randomized. So he's declaring that the thing we can't see has an invisible man property when we have no reason to conclude that. We can't see it, so why should we assume it's made out of invisible men? And that's the same thing with our brains and all science, right? I mean, originally, I'm sure they thought we were full of little demons. Oh, there's voices in my head. There must be more than one little thing working my brain because I can hear voices that say, screw her. And another voice says, no, don't get in trouble with your woman. And, I mean, I have all these voices. Where are all these voices coming from? I mean, so they draw these conclusions. We know that's stupid, okay? And they're doing exactly the same thing. They're saying, there's an effect, and I am going to blame the silliest thing first, instead of blaming something much cruder and simpler. And it's just all over this. They drew a conclusion, and now they're just trying to rationalize the conclusion. But the conclusion was wrong. It's just that simple. They jumped too soon. They're flying off the edge of the cliff, and now they're making a justification for why it was the right thing to do. Oh, the air is so much fresher, and they're making all kinds of excuses for a pretty bad decision.